introduction. So like Greg, I've made the leap from being an engineer to running a company, but still try to keep my hand in on the technical side, and they still let me do things like this. Talk to you guys. So I'm going to be talking about system telemetry and I/O profiling for cloud migration as well as on-prem systems, and in particular how that relates to Singularity. So I'm going to start off with an introduction to Ellexus. I know we've got a few faces in the crowd who'll be very familiar with our products and our tools and what we do, but others might not be. And then I'm going to give you an outline of a customer case study looking at the benefits of I/O profiling and container technology together. So Ellexus is the I/O profiling company, and we make tools to help you understand your workloads. A lot of people think that I/O profiling is just about performance tuning and who's got time for that. But actually what we do far more of is just helping you understand your workloads so that you can make better decisions about how to deploy them, better decisions about what you need for the future. And that means understanding what you need from your shared file systems, what you need from your cloud technology, as well as managing application dependencies. And we generally say that we work in the HPC space, but we're very broad about what that includes. So we work with traditional HPC customers, as well as kind of other sectors such as oil and gas, finance, and actually the customer case study I'm going to present today is from life sciences. So first of all, why profile I/O? First of all, the most important thing you need to do is manage your dependencies. If you know exactly what you need to run your application, then great. Stick that in a container, you're all set to go. A lot of you, I know, won't be in that position. There might be some legacy script that you need. There might be something installed somewhere that somebody set up before they left the organization. It's very easy over time for legacy dependencies to creep in there and for you to not really know what you need. The next reason you want to profile I/O is to understand resources for sizing and resource management. How do you know what to put in your RFIs if you don't know even what you're using today? The next is obviously performance and tuning. Sometimes that is because you've got the resources to put time into getting more efficiency from your system. Other times it's because you've encountered unexpectedly bad performance and you need to fix it. But either way, optimization is something that is often very valuable. And finally, monitoring I/O for chargeback and just really knowing what's normally going on a day-to-day basis. So this is an example of the kind of problems that we solve. This is actually quite an old example now, but it really illustrates well the kind of problems that you can have if you don't look at I/O. So this is a hardware compilation build at ARM, and the application itself is very well behaved, but the problem is the way it's been deployed. And it's supposed to store all of its temporary files on /temp here. But it's not. It's storing all of its temporary files on ARM Scratch, which is expensive network storage. And so this illustrates the kind of problems that can happen when you deploy applications. One of the many reasons why containers are a good idea in order to try and lock down some of those changes so that you get a good idea of how an application is deployed and kind of seal that in a container. And this particular problem was causing huge amounts of issues for the customer, but was very, very easy to fix once they'd actually looked at it. So very briefly, the two tools we have for doing this. First of all, there's Breeze. That is a tool for doing detailed profiling of a single application. that will tell you all of your application dependencies. So first of all, it'll tell you what applications you're running, what libraries you're running. It will tell you if you are accidentally sourcing an installation of Python from someone's home directory. Yeah, we've seen that a lot. And you can then use that to decide what you need to install, either using a package manager system, but also all of those little wrapper scripts and user environment things particular to your setup that you need to include. The next thing it will tell you is what resources you need, so you can size your storage appropriately, and I'll go into that in more detail when I get to the customer example. And finally, and this is very important, even for those who've got a very good handle on what your dependencies are, you can use it to triage problems when you've set up your container and you don't get the same results that you expect. So whether it's some small difference like a missing environment variable, some difference in your path, it's very, very easy for a small change like that to prevent your new deployment from running. And that's not a specific problem with containers, but it's a problem we often see is customers come to us and say, right, we've got this bare metal setup, we've containerized it, it's doing something different, we don't know why, and Breeze is used to do that. So secondly, we also have a product for doing system telemetry. So this is much more lightweight. It won't give you anything like the level of information that you get from Breeze, but you don't want to gather that all the time. Mistral is designed to protect your shared storage by telling you who is overloading the file system at any one point. It lets you find bottlenecks in production, and it also lets you do chargeback to your users. So you can say not only how many nodes did this particular group run on last week. That's something you can get from your scheduler, but also how much of the storage bandwidth did they use, for example. And one of the things that we have introduced, which is quite new, is the ability to kind of take a higher level overview of that I/O profiling data and look at how much time you're spending doing good and bad I/O. And obviously, this is going to be different for different organizations, but we've managed to pick out a set of bad I/O patterns that are just bad for everyone. Small I/Os are really bad for shared storage. They're pretty bad for local storage and even very fast solutions like NVMe as well, and I'll be able to show you exactly why later on. Opening files that you don't read or write from, statting files you don't use, failed file system I/O. So for example, having a lot of locations on your path and searching for resources in all of those locations that perhaps don't even exist inside your container. Very, very easy for that to creep into your environment and slow down the whole system. And likewise, doing that kind of high-level sweep across your entire infrastructure to find out which of your applications are spending the most time doing bad I/O. It's a really good place to start if you don't have many resources to spend on profiling and tuning. And I know most of you don't, right? You've got a million things to firefight on a daily basis. But just getting a quick handle on which of your applications are the worst offender is a very good place to start. And particularly when you're locking down your configuration in a containerized system, what you're really doing is putting in place a new system for the future. You really want to spend a bit of time making sure that that is a good configuration and then build on that from the future so that you don't end up kind of locking in these bad I/O patterns and including a lot of legacy applications that aren't good for your system. And finally, knowing what is normal is so important. A lot of the time, we work with a lot of the cloud vendors. We work with a lot of HPC consultants, and all the time they come to us and they say, we're asked to design a system, and our customers can't tell us what is normal. They can't tell us what they normally run. And so understanding that is the first step to getting a good setup for the future. So this is just a sample taken from our cluster. So I hope that your infrastructure doesn't look like this. This is a lot of very weird workloads, a mixture of sort of HPC and sort of local benchmarks. So we've got metadata per mount point, throughput, CPU and memory there. I would hope that yours is less spiky, basically. And so now I'm going to talk a bit about a particular project that we did with the Sanger Institute. The Sanger Institute are a world-famous genome research centre in the UK, and we worked with the cancer team in particular. They are taking part in the Pan-Cancer Project, which is a project to map 2,000 whole genomes. That is a very, very big project. And although they've got a big compute resource in-house, this project is going to be run across the UK in many different sites. Not all of them are so well equipped with the latest HPC hardware. And so the first thing they needed to do is to take their genome pipelines and make them portable and make them efficient so that they can be easily run in different sites, on-prem and in the cloud. And so the first step was containerisation for them. So that meant tracking dependencies, that meant tidying up their in-house infrastructure so they were no longer dependent on so many legacy in-house things. The next thing was to tune I/O and compute so that they weren't relying on having the latest and greatest in terms of the hardware. And now they need to start specifying what needs to be run, what you need in order to run these pipelines. In order to profile the Singularity containers, it's actually dead easy. So our technology, at the moment, you have to modify the way you run the container or set up the environment in a particular way. So the main thing we need is this LD preload variable passed in. You also need to make sure that you've bound your install directory to something visible inside the container. I believe if you install it in your home directory, that will happen automatically. And then everything else is just passed in. We are working on so the next release, this will happen much more seamlessly. And so our environment will be able to see, oh, you seem to be running Singularity. Let me set that up for you. We're also going to be supporting the Singularity plugins so that you'll be able to just specify -- Ellexus, please. And we're British, so better say please. And then you'll automatically be able to have either Breeze detailed profiling or Mistral system telemetry within your container. So very, very easy to manage this at scale. But that's how you do that today. And this is actually taken not from our tools, but taken from some work done at the Sanger Institute. It's part of that initial step to containerize and optimize their applications, their pipelines. And this was well worth doing. They took the runtime down from 32 hours down to 18 hours for the average whole genome. So huge, huge effort to do that, but a huge win and very, very necessary for the success of the project. I don't have time to go into how they did that, but we do have a white paper with more information about the steps involved in that. The next part I'm going to talk about is taking that optimized container and then working out what the resources were needed for it. So this is the first set of I/O profiling results that lets us see kind of what the pipeline is doing. We just ran this on AWS. We pulled down the container that they've made publicly available, and we ran it on an M5X large image with 4 virtual CPUs and 16 gigs of RAM. They specify 4 gigs of RAM per core, so we chose that machine. And you can see, hopefully you can see it's, I realise actually now, you guys at the back probably can't read that, but at the top we've got the number of I/O operations by type. So the red bar is total I/O operations. You can see most of that is reads. A lot of it is small reads. Then we've got medium-sized reads. Medium-sized reads is what you're aiming for. That's the good stuff. Few writes and not too much metadata, which is good. That is exactly what you'd expect from a genome pipeline. The fact that most of the I/O is small reads, but it's not so dominating the I/O pattern, is a testament to how much work that they've put into that. And just looking at the distribution of reads by size, you can see a lot of it's small reads, but we've also got quite a lot of medium-sized reads up here, which is good. This is very, very good for a genome pipeline. A lot of their algorithms mean that avoiding small reads are very, very difficult, and they've done huge amounts of work to try and aggregate reads that are within the same block. So far, so good. So we next ran the container across different storage options on the same compute node. GP2 storage is the default. That's an SSD, and we tried a bunch of different options as recommended by the AWS documentation. And what we found was that the provisioned IOPS SSDs that are sold as sort of guaranteed throughput, really, really great nodes, for this workload were absolutely terrible. And actually, once so the percentages are normalized against the GP2 default storage, and actually that's the best. Normally for genome pipelines, you'd expect NVMe to be better, and it is a little bit faster, but 10% cost increase for 2% performance increase, it's not a good trade-off. And that's partly because of the optimization they've done, but also because of the I/O patterns and the relationship between the I/O and the compute. So let's have a look and see why we got those results. First of all, you can see magnetic storage is just slower. That's no big surprise. The provisioned 100 IOPS just wasn't, 100 IOPS was just not enough. So you can see here the I/O is being throttled. The genome pipeline, very, very front-loaded in terms of IOPS. And so 100 AWS IOPS is not good enough. And the GP2 storage and the NVMe actually performed more or less the same because, well, they achieved about the same I/O, that's kind of interesting. The NVMe should be a lot faster. So we looked at why that might be. We looked at the CPU, and actually, if you swizzle that on its side, it kind of matches up with the graph that's supplied by the Sanger that I showed earlier on. So always good news. And you can see it's very, very compute heavy, very, very CPU bound. You can see whenever we're not CPU bound, we're IO bound. By the looks of things, there's a sort of one-to-one mapping there. Weirdly, there are not too many IO operations at the end, but also still not too much compute. So why is that? Let's look at the reads. Oh, it's because right at the beginning, we've got loads and loads of small IO, so the amount of data read and the number of reads kind of matches up. And then at the end, we've got not too many operations, but quite a lot of bandwidth. So that's why. So we'll be I/O bound at the end as well. But because we're CPU bound so much, and we actually looked at the memory, we didn't use anything like the 4 gigs that they recommended. We thought we'd try it on more CPU and less memory. So we moved to a C5X large, so that still 4 virtual CPUs, but the CPU is quite a bit faster, about 25% faster. And we found that actually the pipeline ran about 20% faster. So we really, really were CPU bound. We don't have as much memory, and there will be, because it's data dependent, we will find that we run out of memory with some genomes. But the cost decrease is such that it might be, depending on what percentage run out of memory, it might be cost effective just to kill those over after a certain amount of time and then rerun them on a bigger image. So yes, dramatic reduction in runtime and dramatic reduction in cost there for choosing the right compute image now that we now that we know that we've got the right storage. And we can verify that by, again, looking at the I/O patterns. So interestingly, on the same storage, we actually got much better bandwidth with the small I/O on the CPU intensive image. So that verifies, again, actually for small IOPS, it looked like the CPU, it looked like we were I/O bound because the I/O was going crazy and the CPU was not, but actually we were still CPU bound in that section. So that's a really, really important message, is that if you're doing bad I/O patterns, it can look like I/O bound and you're not, you're actually CPU bound because you're thrashing so much to compute the next small I/O operation. And then at the end, we get more or less the same performance with this good streaming I/O, except this little hook at the end. That's where we run out of AWS burst credits. So upgrading to NVMe might solve that. It's probably not worth a 10% cost increase just for that little bit at the end. So that's another reason why it's really good to look at the I/O patterns and understand what the trade-offs are so that you can just see that straight away in the data. So how long did this work take? Obviously, the initial tuning took a huge amount of time, but was worth it for the project. Sizing the compute and storage correctly took 3 days, and that included getting up to speed with the pipeline, and that was so easy because it had been containerized. And we immediately saved 10% of the cloud costs of the project. And if it is viable to use the faster CPU, less memory image for the majority of the pipelines, then we're going to save another 20% on top of that. So it's a nice explanation from one of the researchers that we worked with. Improving runtime doesn't necessarily require extensive rewrites. It's just about knowing where to look. So, what have we learned? So, containers make it easy to deploy applications. I think we all knew that. I think that's why you're here. Optimizing I/O can save you money and can also save you time if you proactively profile your workloads and catch those bad I/O patterns before they become a problem. But you need to actually look at all variables in order to really understand the application. So not just CPU, not just memory. You need to look at the I/O patterns and the I/O performance. So finally, hopefully this will help you get towards your goal of being fast, agile, and hybrid cloud ready. Only that sounds a little bit too trendy for me. So actually, we're still doing what we've always wanted to do, which is to focus on performance, portability, and planning. By agile, I don't mean agile development. I mean just understanding what you're running and being able to pivot appropriately when new technologies come along to help you. And understanding your workloads is about getting good performance and planning for the future. So portability, obviously Singularity, once you have ported your applications to containers, the portability more or less comes for free. Planning is about doing system telemetry. Again, it's that knowing what is normal so that you can make better decisions about how to deploy applications. And performance, great if you've got time to tune for performance. Most of us just wait until something goes wrong and then get rid of that problem. But at least if you're doing the system telemetry, you know what's normal is. You know what you're heading back to. So in summary, I/O profiling is just important for performance and cost. And understanding dependencies is really step one of that. That lets you take control of your data and exploit the benefits that containerization brings to you. Thank you very much.
Thank you. We have time for any questions. Do I see any questions here? We got one right here.
Yeah, thank you for the presentation. I was wondering what kind of support are you providing for the Sankar Institute? Do they develop the tools and then you optimize them, you containerize them, or what is the input to you and what is the output that you provide?
So the vast majority of our customers in the Sanger Institute are within that set. They use our tools independently, so most of the projects, we just hear about it afterwards in a kind of great, we fixed that, thanks kind of way. This particular project, we got involved with doing the sizing on AWS, partly as a project to look at how the AWS storage options compared as well. So it was a kind of a multi-way collaborative project in that sense. But yeah, the vast majority of our customers just use our tools by themselves, and so we offer training and support on that. We occasionally get involved with looking at the data, and that's an important thing for us, because every time we look at the data, we understand something new about it and can add more insight back into the product. But by and large, that's how we work.